So we'll welcome Amir Ahmadain from the University of Cambridge. So he'll give us a follow-up talk from our last meeting about string theory in offshore backgrounds. So we're happy to have Amir, and please go ahead.
Thank you for the introduction, and thank you for the invitation to give the talk. Indeed, this will be the second follow-up talk after Aaron's talk a couple of weeks ago, 2 weeks ago, based primarily on part 2 of our work with this archive number, and then which basically focuses on the black hole entropy, the Susskind-Oberlin black hole entropy in string theory, as an application of the off-shell prescription that Aaron introduced and explained beautifully 2 weeks ago. So this is the main part of the talk. So first, I will, before I get to the plan of the talk, let me introducing. This is going to be an entanglement entropy talk. I would like to start by entanglement entropy in quantum field theories as just one slide. That if a typical state in a local quantum field theory has, as everybody knows, a short range correlations, and the entanglement entropy is sensitive to short distance physics, correlations of modes across entangling surface, which I call sigma here. And this is the reason why entanglement entropy, I mean, there's more algebraic way of defining this as type 3, but in general, we say entanglement entropy is a UV divergent quantity because there is an infinite number of correlations or modes that straddle the entangling surface. And usual way we compute this, of course, it can compute it for a region R as a trace of rho log rho, where here rho R is the reduced density matrix for one particular region R, and where there's an R complement outside here as it is this picture. And this usually is the notion which counts the number of modes straddling sigma, which is the codimension surface. And of course, as we know, it has its proportion to the area of the boundary, and it has some expansion, right? I mean, the leading area expansion has this UV divergent epsilon d minus 2, where d is the dimension of space-time, and gamma is some coefficients that depends on the system you're computing the entanglement entropy for. I mean, this is just very, very rough one-page description of what entanglement entropy in quantum field theories, local quantum field theories, just very basic stuff. But then, and the usual way we learn how to compute this in quantum field theories is we use the replica trick, right? So we say we have an n-sheeted cover of the space-time, and we have cuts corresponding in polar coordinates around rho, and I call him rho and tau. Tau identified with 2 pi k, so k varies from 1 to n. And if we do the typical replica trick, we basically glue the space-time at certain points. We get a flat cone. We get a conical manifold with some angle deficit that is 2 pi times 1 minus n. And then we say, okay, we calculate the trace of rho to the n, and we say this is equal to the path integral on such a conical manifold with flat cones here, right? The typical replica trait calculations in local quantum field theories. And then the usual argument is that we do analytic continuation to non-integer n to be able to actually use the variation formula n minus n del n minus 1 log trace rho to the n at n goes to at n equals 1. And in this, of course, I mean, again, this is very rough. Here we have to use Carlson's theorem to basically make this work for the analytic continuations to be unique. But again, this is not what I'm focusing on. I'm just saying that this is typically what we do to calculate the replica trait of a typical state, to calculate the entanglement entropy in local quantum field theories. And then we define Wn as minus log Cn as the effective action. And then with the polar coordinate tau periodic with period 2 pi n, and we take one of our n to be small, and we calculate the entropy this way. Okay, so this is just replica trait in quantum field theories. Okay, so far so good. Now I'll talk about, since with this introduction, I'll talk about specifically what the Susskind-Uglum did in the paper back in 1994, right? Where they wanted to compute, the goal of that paper was basically they wanted to compute the black hole entropy in theories of quantum gravity, in canonical quantum gravity, and then in string theory, right? And they wanted to do this for the simple infinitely massive black hole, zero in on the horizon, you get Rindler spacetime. So the dimension of such a black hole in this limit, infinitely massive, can be the spacetime near the horizon can be approximated as Rindler, and this is in the Lorentzian signature. Of course, and then you do analytic continuation, the Euclidean signature, tau equals minus IT, the metric becomes this. And of course, when you do the Euclidean continuation, you insist that tau must be identified with beta equals 2 pi to avoid any conical singularities, which would be fake, other than the actual singularity that we know exists in the black hole. So this is what they wanted to consider. And they considered this in the first part of the paper, which is usually what people cite when they cite Susskind-Uglum. This is whenever you see a Susskind-Uglum citation, it's basically citing the first part of the paper, which is the non-string theory part of the paper. But I'll be focusing on the string theory part of the paper, which doesn't get cited as often. But let me first summarize what they did in the first part of the paper, which often gets cited. So before I do that, this is basically just a cartoon for what the Rindler circle would look like if it had a conical singularity here. When I do that, you get the Einstein-Hilbert action as 2 pi minus beta. I'll explain this in the next slide, but this is the typical calculation that they did. So before that, before the first part of the paper, they considered Euclidean quantum gravity, in the semi-classical approximation. So again, take the partition function for canonical quantum gravity, you write it this way, they integrate over the metrics, they integrate over the fields, e to the minus I, and IG phi is basically I Einstein-Hilbert action, and then some matter action phi. Then the typical thing to calculate this partition function, you need to expand the metric around a given saddle, which I denote here by G, and then F will be the fluctuations around the fluctuations of the field. And this is what they did. They expanded IGF in this expansion, and they considered, and then they write down an expansion. The leading term of the expansion is the Einstein-Hilbert action plus the matter action as a function of phi and the saddle point. Then they wrote down Z of beta. They said it can be written down in this form, in this way, at e to the minus beta, where F is the free energy, and then times Z prime, and Z prime contains the integral over the fluctuations. DF is the fluctuations around the metric, phi is the matter field, and they wrote down the Z prime. And then when they do this, the leading term in the action is the Einstein-Hilbert action, and the Einstein-Hilbert. Now I'm going to go back to the slide. The Einstein-Hilbert action with if you do not identify tau with 2 pi, then you will get a conical deficit. Delta equals 2 pi minus beta, and this is an infinitesimal conical deficit. So we're very close to 2 pi. And at the conical tip, the Ricci scalar of such a spacetime is given by this distributional curvature formula, where you have a delta function on the right-hand side times 2 pi minus beta. And then, therefore, the Einstein-Hilbert term naively will be given by 2 pi minus beta times the area, the transverse area of the codimension 2 surface over 8 pi gn, and this is basically the beta f. This is the beta times the free energy. And so the entropy can be given by beta 1 minus beta del beta, acting on log z, which also can be written as beta squared del f by del beta, which gives me a over 4 gn. Because this is something they did with the leading term of the partition function, which is the Einstein-Hilbert term. That's called the leading term, or the classical term in this. expansion of the canonical path integral, the Euclidean quantum gravity path integral. Okay, what about the matter part? Well, the matter part, and this is again the Susskind-Oglum story. The matter part would be as they pointed out in the paper, is that the matter part is considered to be a quantum correction to the leading part on the entropy. And for a massless scalar field, and even for massive scalar fields, what they pointed out is that the UV divergences that occurs in the bare G Newton can be compensated for. It's precisely the same UV divergence that occur in the entanglement entropy in such a way that you can write the entire entropy S as a function of a renormalized G Newton, and you can write it as A over sigma over 4G renormalized. And this is something they pointed out. And the whole point of this is that they say that the entanglement entropy, the UV divergences of the entanglement entropy, as we explained in the first couple of slides, is the UV divergence of the entanglement entropy is intertwined with the UV divergence of the underlying theory of quantum gravity, right? So the reason, the UV divergence that we get from entanglement entropy is really related in this way to the UV divergences of the underlying canonical theory of quantum gravity, and they give this sort of calculation. Of course, this has been done a couple of times for several types of fields, but I think for massive, for fermions, but I'm not sure if it continues to also hold for other non-minimally coupled fields or gauge fields. I think it would. There are subtleties there. But that's the point. This is what usually people cite Susskind-Oglum for. Is the fact that the matter entanglement entropy is a one-loop correction to the leading term, which is A over 4G, and that the UV divergence of the entanglement entropy is related to the UV divergence of the underlying theory of quantum gravity. I mean, this is basically roughly the message in the first part of the paper. Okay, so now we wanted to repeat this in string theory. We said, okay, string theory is as a UV finite theory of quantum gravity. And if it's a UV finite theory of quantum, if we believe that, then we should not be getting the UV divergences. We should get something like a finite dimension of the Hilbert space, and we should be able to compute the A or even the leading term. We get a statistical representation of it from string theory. But then, when we try to do this in string theory, the problem is we now have to deal with the fact that string theory does not like going off shelf. It's not like the quantum field theory. Well, now we deal with it as a quantum field theory on the worldsheet, as Aaron explained 2 weeks ago. But this is the difference, right? It's that string theory is happy about consistent backgrounds and tightly related to conformal field theories. But if we want to use the canonical variation formula, beta 1 minus beta del beta, then we end up then we have a deficit angle, and then we have a conical manifold. Conical manifold is not a consistent string theory background because it does not respond to a CFT. And therefore, we have to deal with these off-shellness in some way in string theory, right? So this is the program, basically. This is where they wanted to repeat. But the difference between string theory and quantum field theory is this. Is the concept of on-shell versus off-shell in that sense. And you see this is basically the circle is not complete. It's like a Euclidean conical manifold where at the tip, the reason it's off-shell is that the Ricci the Ricci scalar, well, in this case the R mu nu is not equal to 0. It's not satisfied. So it's not a conformally Ricci flat manifold. The Ricci tensor is not 0. And as we will learn as we go, this means that there is a graviton pole that does not vanish, which is a one-point function. So concentrated at the tip. And that is what we mean here in particular, in precisely by a background that is not consistent, is that there's a non-vanishing one-point function, which is in this case A01. A00 is the genus 0. Talking about sphere here in the leading term. Maybe I should mention this. Here I'm talking about the leading term A over 4G, which in string theory would come from the sphere partition function. So if I want to derive A over 4G and get some statistical representation of it, I'll have, this would be the leading term, would be the sphere contribution to the entropy. But of course, as Aaron pointed out 2 weeks ago, we know all the peculiarities of the sphere partition function. It vanishes on shell because of the infinite volume SL to C, and I'll review that as I go along. But this is why we needed a prescription, or they needed a prescription to deal with the sphere partition function off shell. And in that case, they cited the papers of one paper by Arkady as a way to actually resolve this problem. And this is why the off-shell prescription or off-shell sphere prescription is relevant in this scenario, is because we want to compute the entanglement, the sphere contribution to entropy, which is the leading term, but then we have an off-shell background because that's a conical deficit, and we needed an off-shell mechanism to deal with this kind of target space. So this is the whole story, and this is the one application that I will focus on, how they did this for the sphere partition function, how they computed the entropy. And let me, in one slide, tell you what it looked like. I'll explain this as I go along. I just wanted to tell you, this is basically the black hole entropy on the left-hand side. And then I have 1 minus beta del beta. And here we definitely use the del by the log epsilon prescription applied on K0, which is the sphere partition function, the sphere partition function computed with with integrating over all insertions at beta equals 2 pi. This will give me Z0, and then Z0 is related to minus the Einstein-Hilbert action, which would be the effective action in this case. Then I get the A over 4G, right? So we wanted to make sense of this. So the first thing that this was the starting point. This is the motivation, basically, to study and justify or prove the off-shell prescriptions. This was the reason why we started to consider the prescription in the first place. It's basically to understand these set of 4 or 5 lines, which, by the way, if you happen to open the Susskind Uglum paper, you'll just probably see 1 or 2 lines. You'll not even see this. You'll see 1 or 2 lines, and that's it, right? Even less than that. It was very tantalizing to sort of try to see what's going on, what the prescription is, justify it, and make sense of it, understand it, explain it, and this is what we did in part 1 of the paper. And now we want to use it in other scenarios, as I'll explain later in the talk. Good. And then we had even a more tantalizing picture of what the microstates of A over 4G would be. If I would like, we proposed a very cartoonish picture of how to get a trace statistical mechanical representation of the leading term, the sphere term, A over 4G, as in this way I have here. So if I want to factorize the Hilbert space, so this is basically, let me explain this picture just in a minute. This is the sphere embedded in target space. And I have the codimension 2 surface, which in this case would be the horizon. And the rotational degree of freedom is basically tau. So each slice is a constant tau, is a constant time, Euclidean time. And so if I imagine a sphere like this from the perspective of a render observer, it would look like open strings with 2 endpoints frozen on the horizon, and they're frozen because there's an infinite time dilation. So they are frozen. And if I were to get such a description of the slicing of the sphere as open strings, then that would give me a trace representation of the A over 4G in string theory without having to without having to, without the need for non-perturbative quantum gravity. I mean, that's whether we'll come to that. I have a lot to say about this as we go along. But this is the picture. Of course, in Lorentzian signature, the Hilbert space the Hilbert space will be factorized as H in and out in this case. And there's a subset here because there's edge modes. We have in states and out states. The left and right wedges around the bifurcation surface, but because there's edge modes, which be these end strings that end on the horizon, these will be like edge modes. That's why there is this symbol not equal, but actually subset of, because we can imagine these the edge modes in addition to the in and out states of the Hilbert space. And in that case, maybe we can write the partition function as on a one-sided black hole. So this will be Z of beta as a trace over the out states, outside the Hilbert space, and e to the minus beta k, such that I can eventually write the black hole entropy as trace of rho log rho, as we usually like to think of. Is this possible? Is this something that we can actually achieve? Well, this is the more speculative picture. So far, it has been very elusive to actually implement. And as towards the end of the talk, I will cite, describe or explain a couple of problems that Aaron and I, given the paper as impediments to basically implementing, getting a realization of such a picture. Okay, there's let me then again very quickly talk about the more well-known way of computing entanglement entropy in string theory that people often cite is the orbifold method. It is an alternative way to calculating entropy in string theory, and it's more well-known and has been around again since maybe Susskind-Oblom. As a matter of fact, the orbifold method was invented, or the first paper written on it was like I think 6 months after the Susskind-Oblom paper, and it has this sort of target space where you orbifold Zn cross Rd minus 2 for n odd. You have a deficit angle, but then the deficit angle, you notice, as again I'm going to explain this later, the deficit angle here is an integer, so it's 2 pi minus 1 over, so beta is like 1 over n, and so the cone has an opening angle of 2 pi over n, and this is something that string theory does not hate. It actually likes because it keeps you on shell. Then you calculate the entropy using d by dn, but then, as we're going to point out, you cannot get the sphere partition function this way. You can only handle the genus 1 contribution and higher, but this way, if you insist on an opening angle, which is 2 pi over n, you will not get the entropy of the partition function unless you add tachyons to the story and tachyon condensation. And again, this is something just I wanted to point out here, something that I will explain the differences between this orbifold method, which is an on-shell approach, to the off-shell approach, or an arbitrary conical deficit, where beta can be anything, any real number, doesn't have to be 1 over n. There are differences, and I will elicit those differences as towards hopefully later in the talk. So with that, I can give you the plan. I will start with a very quick review of the off-shell formalism that then I will use in the second point, where we'll explain how to derive the bulk Einstein-Hilbert action with the dilettante term from the worldsheet sigma model. So I'll explain the details of that. Of course, as far as time permits, there are always more details in the paper. Then I will describe string theory as an induced theory of gravity. Then I will talk a lot more about the Susskind-Oblom off-shell picture, an open string picture, and then I will contrast the off-shell approach versus the orbifold method, and then the very last point I hope to cover maybe is prospects of deriving the RT formula, the holographic entanglement entropy and ER equals EPR, which are all applications that would require computing string partition functions in off-shell diagrams to be able to realize any of these interesting formula, RT or ER equals EPR. So that's the program of the talk. Any questions before? Okay. Okay, so
I have a general question. Maybe I don't know that this is the right time to ask. So you will get the A over 4 GN formula eventually, right?
yes.
Now this GN is renormalized, but that UV divergence is cut off at the string scale. In string theory, it's the GN is the divergences are cut off at string scale, right?
Yeah. Yes. Okay. The derivation that we'll focus on is a gravity derivation, not an alpha prime one. So we'll do it in a gravity regime where the radius of curvature of the target space is much larger than alpha prime in this regime.
Yeah, but I am referring to this statement that you made is that the UV divergence of 1 over GN is cancelled against the UV divergence of the entanglement entropy.
Okay, fine. Okay.
So the GN UV divergence gets cut off by the string scale. So that would suggest that the entanglement entropy UV divergence should also get cut off by the string scale if there is a cancellation.
If there is a cancellation, yes. We haven't tested that, but if there is a cancellation, yes.
Okay. But some of these recent matrix model results suggest that the entanglement entropy divergence is cut off at the Planck scale. So is that a conflict?
I think that as far as I understand, the lure of the Susskind-Uglum implementation is that we have this alpha prime in scale in string theory, which characterizes string theory. I think that this is what we hope to achieve, is that we can get the G Newton at this scale without having to define quantum gravity at the Planck scale. I think this is what we hope to achieve, what we hope to find, and this is what Susskind and Uglum actually proposed, is that they hope that we don't have to define G Newton at the Planck scale, but rather at an alpha prime scale, which characterizes string theory. I think this is part of what we hope to find, actually, if we were to implement this formula as for example, the torus correction would be the one loop correction to the sphere efficient function in this case. I think that's what we hope to find. Whether this will hold or not, of course, that's a different story. But do you agree, Aaron? I mean,
yeah, it's probably worth mentioning that even though everything in this story is happening really at the string scale, because it comes from sphere diagrams, there's a factor of 1 over the string coupling squared, and that's why you get the Planck scale in the formula, even though there's no real Planck scale physics. And
yeah, I think that this issue will come up at the next order, right? When you do one loop correction, for example.
Yes, although in superstrings, I think the torus in Minkowski superstrings, Rindler, I should say, maybe the torus contribution is actually 0, so it cancels. But
yeah, I think if you have enough supersymmetry, but I think if you have n equal to 1 supersymmetric compactification, I think there's a finite renormalization of GN.
Well, I remember reading in Polchinski that in like the 10D supersymmetry, in the 10D string theories, there's no torus renormalization of 1 over T.
I agree. Right? Yeah, I was referring to say 4D n equal to 1 supersymmetry.
Yes, you're referring to the non-renormalization theorems, right?
Yeah. I think if you have sufficient number of supersymmetries, then the correction is 0. Yeah.
Yes, and that also was pointed out in Susskind-Uglum for that particular type, or number of supersymmetry, exactly.
Okay, so in that case, the entanglement entropy should also be finite.
Yes.
Right? If we want the sum to be free from ultraviolet divergence.
Yes.
That is a very strong statement, right? In 10 dimensions, if you are claiming that the entanglement entropy should be finite.
it remains to be seen. I mean,
don't be intimidated, Amber. Own it. It's finite.
No, it's not like I'm going to show or prove it, but it's a strong statement. I agree. It's a strong statement. I'm not. It's a strong statement. It's not been shown yet or proven, but yeah.
Okay.
But it is a statement that Susskind and Ogilvy actually give.
Okay.
Sure. So now I'll start with a brief review of Tetlin's shell formalism, and I think I'll try to cover the aspect that the aspect that Aaron maybe did not emphasize or cover in his talk 2 weeks ago. And again, the central object in the story of an off-shell prescription for a sphere partition function is the infinite volume of the conformal Killing group, which in this case is the SL2C. And it was first pointed out in Lou and Polchinski in the paper in 1988 that on shell, we would expect that the sphere amplitude with no insertions, 1 insertions and 2 insertions to be 0 on shell. Because of conformal invariance and because there is no tree-level mass shifts, basically. That's why the 2-point function vanishes, except, of course, modulo the paper that recently came with Harold and Juan, which pointed out that if I have a string that comes in and comes out, then it doesn't vanish, and it actually it results in a renormalization of the amplitude because of the delta function in the numerator. But modulo that, it's that paper on shell, the A00, A01, A02 is just 0. Because of the infinite volume of SL2C. This infinite volume can be offset, as noted by Lou and Polchinski, that the infinite volume can be offset by some integration that diverges if I were to integrate over the vertex operator insertions. And I think Aaron hinted to that, is that this was the motivation that that led Arkady basically to start actually implementing the program of getting the log divergence of the SL2C from integrating over all vector operator, from all operator insertions, over all operator insertions. So then the volume of L2C will, as pointed out, become from 2 operators colliding, and we have a quadratic divergence, and then we have a log divergence from 2 and 3 operators colliding, as pointed out with some coefficients. And then they also pointed out, as a point in their paper, that the divergence of the volume can be expressed as an IR divergence in terms of an integration of a Euclidean Schwinger parameter in this way, and that you will have a log divergence when would be the Mobius divergence, with SL2C divergence will come when L0 plus L equals 0. It will give you a log divergence. That
sorry, Emma, can I just ask about this? Sorry, are you assuming there's just 3 vertex operators here?
Yes.
I think you might have this back where that the power law comes from all 3 coming together, right?
The power law will give. Oh, sorry. Yes, you're right.
And it's n minus 1.
So the power law is actually, I got them in reverse. So sorry.
Yeah.
Yeah, the power law will come from 3. Sorry. Yeah, that's correct.
Yeah. And the log comes.
Yeah, the log comes from 2. Actually, I reversed.
Yeah.
Thanks for pointing that out. That's correct.
Oh, I know you know this, but
yeah, thanks. That's
eyes on the slide. Pair of eyes on the slide.
Yeah. Okay. So then it was pointed out after this paper, and again, this was I think the motivation that in one particular paper, that if I were to compute the correlation function K0n by integrating over all vertex operator insertions, that I will get a factor in the numerator that is proportional to the log divergence to basically the volume, the regularized volume of SL2C, and then the correct method to basically subtract the log divergence or remove the log divergence is not by dividing, but rather by taking the derivative, and this was not proven. I would call this a proposal. But that we wanted to understand this derivative thing and this derivative operation instead of the 1 over, and this is basically the content of part 1. We wanted to understand why why would you take the derivative rather than just take the log divergence? But as was pointed out by Akari in the paper, is that if I were to calculate the endpoint correlation function of some vertex operator insertions with K0n, I will get such an expansion on the right-hand side. It's an expansion in log divergence, where Bn are basically coefficients that are proportional to the scattering amplitudes. So here they hide the beta functions in them. And that now, if I want to calculate the scattering amplitudes A0n, I would need to take the derivative and rather than 1 over, because there is extra physical logarithmic divergences rather than the log divergence of the SL to C. The log divergence of the SL to C would always be there. It's an overall divergence that always be there. And in that sense, it is reminiscent of what happens at higher genus, because it's like a 3-level mesh shift. From that perspective, it's just always there, but there's always the physical log divergences that Aaron explained, which basically cuts the length of the internal propagators, which also give log divergences, and they would end up with. And so we need to take the derivative rather than the division, because there's going to be these extra factors at the poles. That at least this is the reasoning which was not sufficient for us. And then I would need to do, and then we'd need to feed this into the Callan-Semantic equation. This is called T1 in our paper, the Callan, and we use the Callan-Semantic equation to renormalize all the log divergences and get the form of the sphere partition. It's basically a story in a nutshell. So then I would say this T1, which I will not focus on T2 in this talk as well, because this is the most relevant one to us. It's a prescription for constructing off-shell, low energy, tree-level, classical, sphere effective action for bosonic, but you can also do supersymmetry, but the talk here called bosonic, but he also, I think there's also a generalization of this for supersymmetric case. In the supersymmetric case, for massless string modes, order by order analysis around the flat space vacuum. So here's a sigma model, whereas the proof that Aaron and I gave in the paper did not really use the sigma model. We perturb around any conformal field theory. That could be whatever it is, strongly coupled or whatever it likes to be. Whereas in the original papers, it was a pure nonlinear sigma model that you write as quantum field theory in the worldsheet as a perturbation around flat space-time vacuum. That was the original motivation, and then there was an explicit calculation done to get the sphere partition function, basically the Einstein Hilbert. Okay, so I'm not going to explain off-shell. This is something redundant that, of course, everybody here knows. And then I think I'll just jump to this slide. This may be relevant as we also explain the sphere partition function as a central charge action. As I pointed out, that to remove or renormalize all the log divergences that we get in the sphere partition function, I use the local Callan-Semantic equation, where T here is basically log epsilon. So this is like RG time, T is like for RG time. And then I can write the sphere partition function in this way. And then the thing is this, there's a field redefinition that one can find, a very unique field redefinition such that one can write K0 or the sphere partition function in the form of a generalized volume. Is an integral over d dx square root of g e to the minus 2 pi. There's a particular field redefinition that one uses here in folks that will lead to this form of the sphere path integral. Again, this is not something that we can explain in this talk, but this is just how one can get this K0 as a generalized volume. And the reason it's called the central charge action is that it appears. Let me before I explain that. Now the effective action constructed by what we call the first prescription T1, is then you apply del by the log epsilon on the sphere partition function you calculated, or it has all types of log divergences. And then you get a particular beta function. This beta function, beta twiddle phi, is a particular unique combination of beta functions in field theory space. And it is a combination of the dilaton beta function minus a trace of the graviton beta function. It's a specific direction in field theory space along which there's an RG flow. And it's otherwise you would have to sum over all the beta functions of all the fields there is. But the uniqueness of the field redefinition is it allows you to write the beta functions in such a combination of a dilaton and the graviton. And so this is after applying the Callan-Semantic equation, and this is and then of course then you can see that the beta functions will vanish when the beta functions are on shell or vanish. The action will vanish, right? And then I think as we explained that this is in general true because we have a global shift symmetry in target space-time. The dilaton is a global shift symmetry because the Lagrangian density doesn't have any term that depend directly on the dilaton except e to the minus 2 phi. And so when the beta functions vanish, the beta functions are proportional to the equations of motion. So when the equations of motions are satisfied, the equation itself vanishes. Modulo, of course, boundary terms, which we do not know exactly how to extract from the worldsheet sigma. And the reason it's called the central charge action is a nice is because there is it appears, if you calculate it from the worldsheet, it appears as the leading order term in alpha prime of in this form as the coefficient, this beta phi, the beta twiddle phi. It appears as the leading order coefficient of the Ricci scalar R2 on the worldsheet. The rest are terms that can be absorbed by our RG scheme dependence, and we can forget about them. But the leading term is in this expansion of the trace of the stress energy tensor with this double angle brackets. If you remember the double angle brackets, that would basically mean that you're not dividing by the partition function with no insertions. So we're doing integral, not an average. This is what we mean a double angle brackets in this notation. And so the beta functions appear here, and that's why it's kind of like the central charge of the CFT in the conformal point. And the conformal point, you'll have the beta function of the graviton to 0. And there's a nice story here, but again, this is maybe a different talk. Just wanted to, this is important for what is to come because for RG flow, and that's why I'm just describing the parts that I'll probably need as I go along. Now, with this very, very quick introduction to the original Arcadi's nonlinear sigma model off-shell sphere prescription, very rarely lightning review, I would say, that goes over many papers. I can start to discuss the details of how to derive the string action, especially the Einstein-Hilbert term from the worldsheet nonlinear sigma model, quantum field theory. Okay, so I will start by writing down some partition function of a quantum field theory. The quantum field theory looks like what has the graviton part, has the metric part G mu nu, and has the dilaton part. One could also add the B mu nu part, but for simplicity, it's not in this quantum field theory as nonlinear sigma model action. And then one of the things, so again, the details, there's lots of details here, but the first thing we notice in this derivation is that when we write the measure dx, we write it with as a product over dxz with the square root of the determinant of the target space-time metric. And that this way of writing it guarantees reparameterization invariance, and especially when we add a cutoff. And this is get very technical here. It's an old paper. shows this by Frieden, 1980, that shows that this is necessary to guarantee reparameterization invariance. Then we're going to use in this derivation a different kind of regularization technique, which is the heat kernel, and we'll cut off the action and the measure. And we do this by inserting a factor of e to the epsilon delta. Delta is a Laplacian into divergent expressions, all divergent expressions that we have. And then a major intermediate step. Again, there's lots of, how am I doing in time? Good. A major intermediate step in the calculation is to show that the bare partition function has this following form, product form, if you will, where, and we show the details of calculating each of these factors basically in the paper, of course. Is the first one is the free partition function, z free. And then we integrate over, I think there's a step that I think I missed one step that I should have included here. Anyway, yeah, no, it will come, it will come. And then we integrate over ddy, it'll come to the y mu y. This is basically the fluctuations, the center of mass or zero mode of the string, square root of g, and then we have the dilaton part, the graviton, and the measure part. This is basically the form, the factor for the product form on the right-hand side of the bare partition function of the quantum field theory. So first thing we do, I calculate the measure part, and the measure part takes that form of trace of log g, and it gets n, and this n is very important. Now I define the quantities that I would like because I'm using the heat kernel. The heat kernel kzz is a function of epsilon, takes the form of 1 over 4 pi epsilon times the Ricci scalar times something of order epsilon squared. And the n is the total number of modes, total effective number of modes, that includes the zero mode. So it has the volume over 4 pi epsilon times chi, which is the Euler number, times something of order, the leading order is going to be order of epsilon squared. And the number prime, n prime, would be the one that does not have the zero mode, which is an integral over k prime. And this gives me n, it can be expressed as n minus 1. So notice that the measure factor has this n in it. Now, when I compute, yeah, these are some. This is basically okay. So let me before I comment on the other factors in the partition function, just define the regularized Green's function in the standard way and expand it in some bases, phi m z phi m c prime, and then I have lambda in there, and I have the particular the usual eigenvalue structure of the Laplacian and the orthonormality condition, and then this is just to set the definition if someone likes to follow the calculation as I explained it. But the point is, now we do an expansion by expanding the coordinate x mu into y mu, a zero mode, and then the fluctuations. And then when we do this, you plug this into the expressions for the path integral and expand to some order. And ultimately, you integrate over eta mu, and then your effective action or your partition function will be an integral over y. That's what's going to remain after you have integrated out the eta mu part. And when you do that, you find that the action part, z eta, which is the part that comes when you have integrated out over the fluctuations of the x, times the measure part takes this form, the z free, times the generalized volume. So you see the generalized volume comes about. And of course, chi is here because we're doing this not on the sphere. So let me point out. So I should have mentioned this. We're not. This is for any compact world sheets. So later on, I'll substitute chi to be 2, which is the order number. But so far, it's just it's generic. It's very general. Then I can express my z-bar function as this product. And now what it takes a form of a free part of the path integral. This is just a free functional determinant that has d minus 26 in it in this part. And then I have the d dy, an integral of the zero mode of the string, square root of g. And I have the generalized volume, and I have three parts in here: the dilaton, graviton part, and I think that's it. I'm not sure about this part. Yeah, just the dilaton and the graviton part. But notice that now I want to point out a very important thing is that the measure part.
Maybe it was the measure part because you didn't write that.
What's that again?
Maybe it was the measure part.
Yeah, I think this is the measure. Yeah, this is the measure part. Oh.
So it's just what immediately follows.
Yeah. Just to correct it later. Thanks. So then, yeah, this is the measured part. It comes around here. So the measured part has this expansion. And notice that what shows up here is the total number of nodes n. That, of course, meaning the effective total number of nodes, which include the zero node, times the propagator. This is the propagator that comes from, let me remind you, of the regularized propagator of the Green's function. So dzz. The dilaton part, so this has a logarithmic divergence right here. The dilaton part takes also this form. And then the graviton part will have to evaluate these diagrams, where by this notation, this means that we identify this leg or that leg. So this will mean by, identify the derivatives. And we give details of how to calculate these coefficients, J1, J2, J3 in the paper, but they each have log epsilon divergence in them. And notice that they have n prime here. So J1 has n prime, J2 has n prime from the graviton. And notice that the measure part has n in it. So the measure part has n, while the graviton part have n prime. And so when I put things together and evaluate this expression that I started out with, this is what I want. This is what I wanted after measure, graviton, dilaton, the free part. When I put things all together using this heat kernel regularization method, you find that, interestingly enough, that you have this sort of expansion where
You define n prime for people.
I think I did. Really did.
It just excludes the zero mode. Yeah.
Yeah, I did it here. Yeah. And this excludes the zero mode. And so then you find that n minus n prime shows up here, log epsilon. This is, and then times dzz. This is just a constant factor that one can forget about, times the logarithmic divergence. This comes from the dzz part, which comes from here. And then you have n minus n prime. So all in all, you'll have the zero mode is very important. The zero mode here, in this case of the Laplacian, is what gives it, what makes this non-zero. This is why I wanted to highlight this. This is one of the important points in the derivation. The zero mode that basically lead to a non-zero vanishing partition function, in this case off shell. I mean, you can see it. You can see that the graviton part has n prime, and the dilaton, while the measure part comes with n. And it is this combination. They come together in and again, there's lots of details at this point, but after it's all said and done, you get the sphere partition function with the correct dilaton term, and with the log divergence. All what needs to be done now is to simply, at the first order in alpha prime, is to simply apply the del by del log epsilon prescription to the K0. And when you do that, you get the sphere effective action to first order in alpha prime. I guess one can say here, so Then of course, these are the beta functions. We can express the R, this is the Ricci scalar, so one can express this is in terms of beta functions. This is the R mu nu is the beta functions of the graviton, and this is the second leading term after the d minus 26 of the beta functions of the dilaton. So these R and grad squared phi. And then you derive the Einstein-Hilbert action. Of course, where is the boundary term from that story is something that is, I don't know how to do. All what I can say is that, and there's again more details about that in the paper, is that in order to obtain this, there's a step that to get the R is that we have to integrate by parts in Z0. Throw away the following three total derivative terms. These are three total derivative terms that, I mean, it's an elaborate calculation that one has to generate during the while deriving the Einstein-Hilbert term. Notice that I'm not sure if this is interesting or not, but maybe someone will have more insight. Is that the first total derivative term is actually, if I were to write it in as a boundary, assuming there's a boundary, this will give me trace K, the first one, actually, by some known gravitational identities. I'm not sure what to make of this, but this one is trace K.
Amir, sorry for the interruption. Just a warning for 10 minutes.
I have 10 minutes.
We'll have questions and so on.
I have 10 minutes left?
Yeah.
Okay, just thanks. Good. So let me point out in target space, the classical, this is the one slide that I started with. In target space, the classical string action can be written like this. And then we know that the action vanishes because the dilaton equation of motion can be written as in this form. It's proportional to the action itself. And so one can actually write the action in this form using the dilaton equation of motion. For an asymptotically flat solution, the boundary term at infinity using the lowest order terms in the action can be expressed as such. As the integral over the boundary, square root of h, there will be induced metric, e to the minus 2 and here I've added the Gibbons-Hawking term, which can be written as a normal derivative of e to the minus 2 square root of h. Right? This is any asymptotically flat solution, and this would be the on-shell sphere partition function. This would be the value of the on-shell sphere partition function. How would...
sorry for the interruption again. I was wrong. You have still 30 minutes.
Okay.
I'm sorry.
No. Thanks for it. I thought I had 30 minutes, and so
no.
Okay. Thanks.
Yeah.
No problem. No worries. Thanks. So how would one derive this boundary term with the Gibbons-Hawking from the worldsheet? That I don't know, and I'm not sure also if there are any progress. There's any progress in that from the string field theory point of view. As far as I know, there isn't. All what I could point out is that during the derivation of the Einstein-Hilbert term, as I explained, one has to integrate by parts and get these total derivative terms, and the first one happens to be trace K. I think also the second one has a bit of unusual index structure, but the first one is definitely trace K. So that's what one could possibly say here. Maybe people in the audience will say more about this. Okay, so at this point, I will start talking about the second part of the second part of the talk, which is the second part of the paper, the second part of part 2 of the paper, which basically discusses some ideas related to how the problems in realizing the open string picture in Soskin-Oglum, and comparing the orbifold method to the on-shell, to the off-shell method, and then talks about some prospects for deriving, applying off-shell string theory in the bulk in a holographic context. Basically, this is this is the second, the next maybe 30 minutes that I have here. Probably even I'll need less time on that. But it was also one of the points that were also raised and pointed out in Soskin-Oglum is that string theory is an induced theory of gravity, and what by that Soskin-Oglum meant that the string action does not stand on its own in target space. It comes from the worldsheet. It's induced by the string worldsheet theory, right? In the sense that if I want to couple strings to gravity, we don't have an action like looks like this. We don't have an action that I have a separate independent strings action, and then I have the Einstein-Hilbert term. No, there's no such action. Everything comes from the string action comes from the worldsheet. In that sense, it's induced. And then, so if you have the fundamental description, then the bare value of the dilettante is 0. Only in an effective theory, then we have the 1/gn is not equal to 0. Again, this is something that mostly reminiscent, modally equivalent to Sakharov's induced gravity scenario, where Gn is induced from at one loop matter conformal field theory, quantum field theory at some UV cutoff at LP. And that string theory does better because, as we know, G Newton is proportional to Gs squared. That would be like the string, the sphere partition function will be sphere because of Gs squared times the alpha prime, basically LS and the string length with a D-2, right? Because so the hope is that we can say something about G Newton in string theory because it has this length that basically makes it distinguishes from other theories of quantum gravity. Implications for black hole thermodynamics is that if I have a black hole that is coupled to some quantum field theory, they would have this generalized entropy. This touches on the point that Ashok, started with the beginning of the talk. That if this is true, then the generalized entropy will be A over 4G plus S out, and S out would be trace of rho log rho, the matter part of the entropy. But then if the Soskin-Oglum idea, is true, we believe it, then the entire entropy is going to be S out. And that this includes even the black hole entropy, right? If we were able to get a statistical representation of A over 4G, it will be entirely S out in the sense that it has a trace representation, and that this requires, of course, to write. So this would be the repercussion, the implication of that, right? The consequence of having the statistical mechanical representation of the black hole entropy. It requires the Hilbert space to factorize in string theory, that is to say, explicitly realize the open string picture. Note something, just a quick side note, is that in the induced gravity scenario does not explain the Einstein-Hilbert term on the world sheets, right? So you might wonder if there's something more fundamental than that, right? That when we write down the Einstein-Hilbert term in the world, we don't know where it comes from. I mean, it doesn't have an explanation for this. This produces the 1/g² factor, but anyway, we'll these are again more speculative points, but just wanted to point out that this term on the world sheet is there. It doesn't have an induced explanation as far as I know. Now, before I get to the other orbifold versus on-shell, I would like to talk about on-shell versus off-shell thermodynamics. On-shell, the Einstein-Hilbert action, again, sphere part, contribution, is that the Einstein-Hilbert term 0. The classical black hole entropy will come from boundary terms. And the on-shell method, the difference between the on-shell method in the thermodynamic sense is that when you take the del by del beta variation, it takes you to a new saddle point. So in the sense that you move to a new mass as a function of the temperature. In other words, simply, i.e., is that if I change the temperature at infinity, I allow the geometry at the horizon to basically react to the change in temperature, so that they are coupled. The mass is a function of beta always, right? So I change the temperature or the inverse temperature at infinity, then I allow the geometry to react, and they're coupled, right? And that's why we say the thermodynamics, which is the usual way to think of thermodynamics. This is the on-shell way. When I go off-shell with thermodynamics, things are bizarre, because what we're saying is that now I'm decoupling the temperature from the mass. Right? The del beta f is independent of the mass. The geometry does not react to the beta variation away from beta equals 2 pi. And this is introduced as a conical singularity. So the meaning of introducing a conical singularity at the black hole horizon in an off-shell way is basically decoupling the beta variation from the geometry. So and that way the background is inconsistent. That's basically morally what it means. So now we talk about several issues in the second part of the paper. Is that if I have a conical singularity, what one can imagine can excise the conical singularity and change the topology to that of a cylinder, because if you do that, then you'll prevent the spherical worldsheet from actually crossing the horizon. If you just cut it like that, what needs to be done is to regularize, use a cutoff, and start a regularization procedure. And in a matter of fact, you'll have to see if there's such an RG flow from a cone with a distributional delta function. So with Ricci, the entire curvature is concentrated at the tip of the cone, and then study the RG flow on the worldsheet, and then see see the tip smooths out all the way to flat space, right? And this will give you like beta equals 2 pi limit, the on-shell limit, right? And so is there an RG flow of that sense from a conical manifold perspective? Is there an RG flow? You can start, of course. One can study this kind of RG flow is known, I think, as smoothing RG flow. This is a beautiful reference there. It's a PhD thesis in mathematics that has a lot more details on this kind of setting up this RG flow for conical manifolds. And it says this would be a unique limit where the cone flattens out. And so you study a typical RG flow in this sense. This is a Ricci flow equation, and then you can write different conformal frames. You can write the metric in a conformal frame in this way, and then the metric on the cone in some particular kind of coordinates will be written in such such a way where the AT part is a finite bounded function, but all the information about the conical singularity is basically in this beta log R term. So this is again from the thesis, and so one can want to set up such a problem numerically and try to solve and see what happens to the cone as the curvature at the tip diffuses all the way to space-time. The subtle point here is that the integral of the Ricci scalar is constant, right, in RG time. So 2 is because of the Euler number. So it's always a constant. So as you move away, so suppose you define a conical singularity at a particular UV cutoff epsilon, and then as you RG flow to another scale greater than epsilon, this is always going to be true. This equation, this integral of R is always going to be true. And you see that R still spreads out and goes to 0 every point in the manifold if you take epsilon goes to 0. And so again, I haven't set up this problem of RG flow of the cone yet, but one hopes to actually study what happens. And this is very important. Maybe it will shed some light on the boundary term of the sphere, but one has to study, in fact, the RG flow of the cone in such a sense and see what happens as the cone flattens out. So again, I mean, and again, this is the open string picture. And as I mentioned in the beginning of the talk, there are challenges here. And let me point out that at least, I don't know more than what I'm going to say, is that there are a couple of very serious problems that one has to deal with if there is any hope maybe of realizing the open string microstate picture of the leading A/4G term. One of them is that of a boundary conditions. So if you imagine the string worldsheet cutting across or crossing the horizon at several points, what you would want to do is to cut a small disk D at every point P that on the worldsheet. Here, sigma is the worldsheet, not the entangling surface. Horizon is the codimension to entangling surface. So you want to cut a disk at every point on the worldsheet that crosses the horizon, and to regulate it. And for this to work, you want to ensure that the trace of the partition function z of beta, which is trace out e to the minus beta k, you want to ensure that this partition function, one-sided partition function of the unpunctured sphere, is equal to that of a punctured sphere. As a matter of fact, I think I should say that this picture is very naive, in the sense that as you move in and look closely into the horizon, you find that the sphere does not really intersect the horizon at 2 points. It's very fuzzy. It's very fuzzy. There's a UV divergence problem, and you find that actually the worldsheet sphere intersects the horizon at an infinite number of points due to the UV infinities. And so it's actually an n-punctured sphere, right? And then, or if you actually even, it's not 2 points, it's an infinite number of times, but if you're willing to say that infinity is like, there's a finite number of points where the worldsheet sphere intersects the horizon, it's an n-punctured sphere. It's not a 2-punctured sphere, as you look closely, because it's a UV divergence problem. And this brings me to the other, sorry, whoa, I think I made a mistake. I'll explain. This is the other problem of the UV regularization of x mu. At any point on the worldsheet P, the x mu is infinite, and this was pointed out by Susskind, by Lenny Susskind back in 1993. As a fact that this is a problem in string theory, that on any point in the worldsheet, if you take the expectation value of x mu squared, will be infinite, and that we need a regularization, we need a regulator. But luckily, since we have been discussing UV regulator on the worldsheet, one can hope to use it to solve this infinite number of intersection problem of the worldsheet intersecting the horizon infinite number of times. One way to do this is to add such a term called stiffness term, or we define it as a stiffness term. You would add a term like that to the worldsheet action. And what effect of this term is to actually regulate the UV behavior of the propagator. So instead of the propagator being 1 over p squared, it will be 1 over p squared plus 1 plus p to the 2m, so you modify it in such a way, and that will give you the stiffness of the string. Will make the string stiff such that in target space it does not intersect the horizon in a fuzzy way at an infinite number of points. One would hope to actually study such a worldsheet with such a term and see what it actually does to the UV behavior of the strings in target space. This is again one problem that we're aware of, and here's the proposed solution to this problem that one hopes to actually implement. Let me also point out that one can get from the Susskind-Oglum open string picture, ER equals EPR. If we were to imagine each point on the worldsheet that has a disk, and as I said, this is these open strings are considered to be constant time slices in the rotational direction. They are constant time slices. And if I imagine having a disk around each point where the worldsheet intersects the horizon, and I put some consistent boundary conditions on it, Each endpoint, I mean, you would imagine that I have part of the disk outside the edge in edge in, and part of the peer disk is an edge out. So, and it is an entangled, they're entangled. So we have inside the horizon, outside the horizon, in the Rancian signature at least, at the bifurcation surface. So in a sense, this would be a realization of if ER equals EPR, if we were to get the open string picture of the Susskind balloon. Okay, then I will quickly, in the remaining few minutes, contrast the orbifold method to the off-shell method. As I pointed out in the beginning of the talk, the target space here is like a complex, the complex plane modded out by Zn, where n is some odd number, quotient out by rotations over angles, which are multiples of 2 pi over n. It's no more orbifold. Of course, again, the orbifold has a singularity that you can think of as a conical singularity, a real conical singularity. The point is the opening angle has 2 pi over n, right? And n is an odd integer. And this is what keeps string theory on shell versus the arbitrary value of the conical deficit, which can be anything, right? Now, the orbifolding introduces also twisted states, which states have 1 in numbers k, n1 to n minus 1. And these 1 in numbers are conserved mod n. So if 3, this will be a k mod 3, for example, if we choose the orbifold to orbifold by z3. The ground states are twisted tachyons in this orbifold theory. In type 2 string theory, orbifold has twisted tachyons, for example, with this kind of mass, with this mass. And the important point is that then you can, inspired by the replica trick in quantum field theory, the orbifold computes this entropy, right? For genus surfaces, for genus G surfaces, which for genus which is greater than 1, so it does not include the sphere. And you do d by dn and zg of n at n equals 1. Where rho 1 is here the Rinder state defined by n equals 1. So most of the literature which uses the orbifold method to compute entanglement entropy in string theory take the original background before the tachyons condense. Right, and I'll comment on that in the next slide and hope that n equals 1 limit the tachyons do not matter too much. So let me point out a very important difference between orbifolds without tachyon condensation and the off-shell method. As I pointed out, orbifolds. So let's take a look at these two figures. I have a figure on the left and a figure on the right. The figure on the left is a 2D, the one on the right is a 3D. The blue point here is the orbifold singularity. This is basically a Z3 orbifold. And I imagine I have a closed string with k equals 1 that ends on the surface here with 2 red points. In the three-dimensional version of the picture on the right, I imagine the sphere, which is this red lines, right? And then the black lines would be basically the time slices, and this would be the string pinching off, at this orbifold points. In an orbifold, the strings. This is one major difference between orbifolds and off-shell arbitrary beta are not allowed to pinch off at the singularity at all, and that's because the twist number is conserved. K is conserved mod n. So they're not allowed to pinch off at the singularity. But in the arbitrary off-shell case, where you allow the conical deficit to be any small real number, again close to 2 pi, the absence of this process, right? This process is allowed. This process is allowed. It's not allowed in the orbifold at all. The absence of this process is also why the analytic continuation of the orbifold method to arbitrary beta does not have a geometric interpretation. So as we know, the whole point of using the orbifold method to compute entanglement entropy is the success lies in the success of the analytic continuation to real beta, or to real n, right? And this is something that has to be figured out in general for this method to actually work, because there are two different ways to compute entanglement entropy. Either I give you a method that you trust. This method will allow you to compute partition functions directly on off-shell backgrounds. So, okay, then you don't have to deal with the analytic continuation methods at all, because from the very beginning, you're calculating on off-shell backgrounds with arbitrary values of the conical deficit. Or you stick with the orbifold method, and the string theory likes to be on shell, but then you'll have to deal with these differences. And more importantly, you'll have to figure out the analytic continuation to non-integer n or beta, right? And figure it out. In a sense, you're going off shell when you do analytic continuation, because you're moving away from an integer n that string theory likes to keep you off shell. So when you do analytic continuation, you are in a sense of going off shell. Of course, as we point out, we'll probably don't even have a geometric interpretation in this case. So yeah, already mentioned this point. That it's for this reason that it's implausible for the orbifold can be interpreted as a thermal partition function at some inverse temperature beta. I mean, again, let me, for the interest of time, talk about orbifolds with tachyon condensation. So I'm sorry, I think this should be with tachyon condensation, not without. Here, this action was again suggested by a paper in 2001 by Tish, Double-Car again, where he included the tachyon condensation term. So you see this delta function there times the potential of a tachyon, and then the Gibbons-Hawking term, and then using tachyon condensation, he at the lowest order in alpha prime, the tachyon potential sources the conical singularity. Remember, so when I go off shell, I should have said this from the beginning. When I go off shell in the Susskind-Oglum way, there's no source for the conical singularity at all. There's no source, nothing sources it, right? The tachyon potential added to the action, right, on an orbifold sources the conical singularity, right? In such a way that allows you to write the conical deficit is equal to 8 pi gn times p of t. And the idea was, if we follow all the way to the infinite, to the infrared, then the entire contribution will come, because we're on shell, the bulk term vanishes. The entire contribution will come from the Gibbons-Hawking term in such a way that one can write the free energy as 1 minus n over 8 pi gn. Let me point out that with tachyon condensation, no, I'm not sure if you believe in this, in the idea in the paper or not, or you trust it or not, but when you add tachyons to the story, the tachyon condensation will definitely heal the orbifold singularity by allowing the Crenshaw process that would not be otherwise allowed without tachyon condensation. So that's important. That's important. So the tachyon condensation is important here, and what brings it closer to the arbitrary off-shell method that we discussed. Again, I'm not gonna. There's some ideas about how to do that in Miracle's EPR, but let me end up with some concluding remarks in future directions. Good, doing good. That in perturbative string theory, we can compute with some caveats in off-shell backgrounds, as we at least showed, hopefully convince you. Now we're trying to extend this formalism to Lorentzian backgrounds, and there's active research in that direction, but we don't know what the boundary term is of the sphere partition function, especially in non-compact conformal field theories. We don't know what the boundary term is or how to derive it from the worldsheet to be actually specific. What is the boundary state, at least if you imagine even naively that the sphere intersects the horizon at 2 punctures, what is the boundary state? More importantly, something I'm currently thinking about and working with some people on is how to derive the RT formula in string theory. Suppose you take ADS3 cross ADS3 CFT2 and one of these beautiful alpha prime exact models. How do you one can derive the RT formula or develop like a trick in string theory? So can we find such an operator on the worldsheet in an alpha prime exact regime that inserts a conical singularity in target space? What is that operator that one can find? So let me for example say I want to have a low quote small decimal proof of the RT formula, right? So this is basically a very rough four steps of the low quote small decimal proof of the RT formula, which they gave in semi-classical gravity in 2013, right? Suppose I want to naively implement this program in string theory. Say something about the RT surface in an alpha prime exact regime and see what the minimization, what we're minimizing over, what happens there. At some point here where we introduce in step 3, the conical singularity, at the tip, we'll have to go off shell at some point. First of all, I have to determine what this operator on the holographic CFT that inserts a conical singularity in the bulk, but then I'll have to compute on backgrounds of the conical singularity and go off shell in that sense, and then show that as we flow to the semi-classical limit that have maybe, because there's no area in an exact alpha prime regime because it's strongly coupled. I mean, alpha primes is the order of the radius of curvature, but then you hope as you flow to actually see the multiple saddles that you can minimize over. I think I'm inspired by, I have to say, by my conversation with Ashok I think a month ago on this, and I'm pursuing this actually seriously these days with a couple people at Harvard. So trying to actually make it concrete as an application of off-shell string theory in the book. Again, one can hope to get ER equals EPR, get the island story and the radiation, and try to do string theory in this discrete background. Is it possible? I don't know. It's a stretch, but maybe this would be easier. So I start with an off-shell wormhole, and then I do Z orbifold. I get once a plane. I get a complex plane, one plane with a tube with this sort of neck and a disk on top. This is like one part of the wormhole. This will be the APR part. Do RG flow from this configuration, and if we land on something smooth, that will be the ER. So this is something one can set up and realize. I think it's not out of reach, maybe, but some realization again. And with that, I will end here. Thank you so much for listening.
Thank you, Amir, for the nice talk. I apologize again for the mistake.
No worries at all. No worries at all.
Just a momentary confusion. Are there questions from the audience? So someone is raising their hand. No, I don't see anything. If I stop recording, would there be more questions?
Maybe.
Some people are shy. Okay, so let me do it like this. We can finish it off, and I'll stop recording, and I'll leave the room for questions and discussions if you.
Okay.
Yeah. Okay. Thank you again, Amir.
Thank you. Appreciate it. Thanks.